а я их...
Хорошо, значит, я тогда включаю запись. И через некоторое время можно... Значит, пока определено понятие кластера, приведены примеры кластеров. И последний пример был, мы берем некоторое z и берем все, где все оборвалось, все y, видимо, на расстоянии не больше, чем m от этого z. Нет, это
Сейчас.
не будет кластером, потому что...
Нет, значит, давайте я перейду на другую страницу. Вот, значит, кластер, который, значит, слушатели изобрели. А Брюно нету, мы по-русски говорим.
Oh, yeah, sorry, Bruno is here. Don't, we
Okay,
can
so
ask
so
him to...
so yeah,
Yeah.
we have just sorry, I
I can
second.
interrupt if it's too difficult.
No,
Okay,
it's not difficult. We just
just
no, no,
we
no
have
problem.
okay. You have invented the idea of a canonical cluster, where we have some core or kernel Z and all possible. Oh, I forgot the word. Лепестки,
Petals.
petals, all possible petals uh, are next added to this core.
On arXiv, I've seen a paper from Epstein with also such a strange thing, but I didn't even read the abstract. But
Yeah.
do you know about it? Ah, okay.
Yes,
That's
yes,
good.
yes. I know about it, and actually he knows him. He even he cites our old paper just by myself and our paper with Andrei Muchnik. But Epstein, it's some or Epstein. Okay, this guy is a more advanced version of this story. Okay, so here all these petals are of size m, and then what we get of this sunflower is a natural example of a cluster. Next question. Okay, you have invented this very nice and natural example of a canonical cluster. Can you invent some other example of non-canonical cluster, any kind of non-canonical cluster, but with the same request? I want the size to be close to the diameter. Ideally, the size should be the diameter minus a constant, or at least something close to this. If it is a minus log m, it's okay. Maybe even 99% of m is still okay, but something which doesn't look like a sunflower. Of course, we can just eliminate some elements from the cluster, just kill some of this 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 лепестки значит, лепестки в
Petals.
ромашке,
Yeah.
petals in a flower, and just take some subset of a canonical cluster. I don't know. We can kill 30% of elements in a cluster. It still looks like a cluster. Just the size is getting a bit smaller. But the question: can we do something completely different? Not just a dense enough subset of canonical cluster, but something completely different. Okay, here is a picture which is somehow suggests that there must be some other examples. So what we have seen, this canonical cluster, is somehow metaphorically represented by this picture. So there are many petals with a common kernel. One reason why they could exist some different clusters. It could be a picture like this. So you see here every two elements have a large intersection, but they don't have any common kernel. Another reason why they could be clusters with no common kernel. We know from the paper by Gutch, Kerner, and many other papers following this idea. Even if we take two strings, two objects with a large mutual information, it is not guaranteed that this mutual information can be extracted and materialized like a kernel, like a common part of them, even for two objects. And if we have exponentially many of them, there are maybe even there are more reason to have constructions of clusters where every two elements share huge mutual information, but we cannot capture it as this material kernel.
So does this example with projective plane works over finite field? So then the strings are the lines of the plane, and any two lines share a point, or any three lines share a point, but for different triples you have
if
different
any three
points.
It's a very good example, because if any three lines share a point, this is the same point, because if the crossing point of A and B is shared with any third line C, then this crossing point will be a common point of all the lines. So
so it needs to be a special set of lines to make a counter. Okay, so it's not.
Not sure. It's a good. Just here's the point of Bruno is that it's a kind of it's another point of view, but it turns out that it's again a sunflower with a kernel. So we have different lines going through the same point.
Or just let's take a normal plane over finite field, and then take a square. So two parallel lines and two other parallel lines, and then.
No, if the parallel lines share, of course, it's a lot of information, but they don't share any information with the other two parallel lines.
Okay, if they're somehow orthogonal, or in some sense, the direction the slopes can be computed from another, then indeed they will share lots of.
But this information would be exactly the slope.
Yeah. Okay. Sorry, stupid idea.
No. Also, I can add another stupid idea. Imagine we take a random string, and then change a small fixed fraction of bits in this string. And so.
Okay. So let me. So this is the Boolean cube. This is a Boolean
just
cube.
As a sphere is a ball in a Boolean cube.
Here is a point, and we take a sphere of some radius in this Boolean cube.
Yeah.
Sasha, but the distance is twice as large as the radius, and that's a problem. So we do not obtain a dense cluster.
No, not exactly twice. The distance will be twice, but informational distance will be not exactly twice, but still
less.
Yeah. So the points are close to each other up to some 2 epsilon, and this makes the distance small somehow, but not enough points we have, because the requirement to be close to the center is a stronger requirement. So we had only few points compared to what we can have according to the distance.
Yeah. So here the log size is much smaller than the diameter. Okay,
No,
so
much smaller means that half of a diameter or 3/4
yeah,
of the diameter, something like this.
Constant times smaller than diameter, not just m minus a little bit. Okay, so we have a difficulty. We are trying to invent some non-trivial example of a cluster, and we are failing. And there is a reason why we are failing. We fail because there is no dense cluster which looks like this. All dense clusters look like that. And here is our main result. Every dense cluster is, just in the sense of information distance, is a canonical cluster or a large subset of canonical cluster. So this is the statement. Or if you want to be more formal, here's the formal version. Just I will let you read the text. Just the same thing. The same I have told you, but with the formulas, and we specify the precision. The precision is logarithmic.
Yeah, so the difference between size and diameter is d. So d is somehow small, but then the d is just copied in the bounds for canonical
D
cluster
is a kind of deficiency. D is a difference between log size and diameter.
So if it's very close, like log n or something, then we know that the string z will provide kind of logarithmic cluster of the logarithmically bigger size.
Okay, any comments or questions about this statement?
So do you also know that the parameters are tight?
You mean
So you cannot replace d by log d in these two inequalities. Is it possible that some more clever argument you can replace d by log d in one of the two inequalities? Or you have counter example using non-extractability of mutual information, of common information, mutual information.
Okay, I don't know.
Okay.
I suspect that it's impossible to get better tight inequalities, that inequalities linear in D and logarithmic in M. But I'm not ready to explain why.
No, if we have this example of a ball in Hamming space, that it seems that D is more or less kind of, I don't know, part of linear proportional to length, and it's not. I think that it's difficult to find some cluster which would be of logarithmic quality. I don't. It needs to be proven somehow, but that would be strange. Yeah.
Yeah, it would be strange. Yes, but I cannot explain you immediately why this is impossible. It would. I expect that this is impossible, but I cannot tell you why. So once again, the message of this talk: this picture is impossible, and this picture is the only way to get a dense cluster. Now we can do two different things, any of it or both, one after another. First, I can prove this theorem, and it's not terribly difficult, but I guess it might take all the time that we have till the end. Or we can use this theorem in some application, just to show that in some kind of a result in the spirit which is opposite to Gaussian kernel, we can show that in some situation for some triples of strings we can also materialize their mutual information. We can common information is substantially equal to the mutual information. So what do you prefer, the proof or for an application right now?
No, since people are not probably did not try both, so I think in my advice is to look at the proof first, because it's a kind of a proof of type which is not very. I did not understand. It's something untypical, and I think it's worth trying to understanding what is happening.
Yeah, and
Vereshchagin also wants proof.
Proof. Okay, proof. Let it be proof. Notes. Okay. We start the proof with a couple of trivial observations. The first trivial observations, I call it a lemma, but actually it's a really simple idea, and it has nothing to do with clusters or information distance. Just some basic statement about mutual information. About Kolmogorov complexity. Let us have two. So what I'm trying to draw a picture illustrating the statement of the lemma, not the proof. I assume that we have two strings x and z, and we have many strings. Let us have many strings y. And for all these strings y, we have the following property. Complexity of y given x is at most v, and complexity of z given y is at most w. These two conditions. And there are lots of this y. There are 2 to the u such y. Then complexity of z given x is bounded more or less by v plus w minus u. That's some logarithmic terms that we can ignore. So once again, if so we will apply this observation in the situation when v and w and u, they are all approximately the same. Then in this inequality we will have n plus n minus n, which is only 1 times n. So if we have many chains with 2 steps from x to y and from y to z, then complexity of z given x is small.
So the triangle inequality becomes stronger if there are many triangles. Somehow.
I can do that. Yes.
Also, I can remind. It reminds me there is a statement: if a string has a lot of program of some length, then it means that it has even a shorter program. So shortest program should be unique, and here is some kind of the same type of statement.
Yep. Okay. If you are with me, do you understand the statement? Are there any questions about the statement of lemma? I think everyone is happy. But maybe then somebody can explain the proof of the lemma, why this so-called lemma is true.
we can try the same argument as in that other theorem. Probably
No,
the number of
trivial thing
z.
is that x is just a condition, so everything can be relativized given x.
Yes.
So we can forget about x.
Indeed.
What is the symbolical picture showing?
Okay, this symbolical picture shows that for 1x there can be several different strings y with this funny property, that there are many paths of length 2 from x to y with complexity v on the first step and complexity w on the second step. There can be many different y with this property, but not too many. Just
So our goal is to show that all these y's can be enumerated given x and the numerical value of v and w. So if we know that there are not too many of them, then we can encode each of them in a short way.
Yeah, of course.
So maybe someone will finish the proof. Misha, can you finish the proof?
To me?
No, any Misha is okay, but
No, I don't.
So why it cannot be so many y for which there are many paths of this type?
That's because the total number of paths is small. It's 2 to the power v plus w, I guess.
The total number of paths is 2 to the v multiplied by 2 to the w.
So sometimes we go through the same intermediate point, and some go we go in different intermediate point. So we have total paths, two steps paths to the sets to y's with the given property. There are that many of them.
Yeah, let us also draw.
And every path leads to a single z. So the number of z's with that many paths is obtained by dividing this number by how many paths leads to z. It's so trivial, I would say.
It is trivial. Yeah, I agree.
No, but это самое, это жалоба или благодарность? This is a good thing or bad thing?
No, it's not a complaint, for sure.
This is the number. Okay, an upper bound for the number of y with this property that we have many chains of length 2 that follow to this y. So to specify the real y, we need to know its ordinal number, its index in the enumeration of all suspicious similar y.
To specify z, I guess.
Yeah, sorry, to specify z, yes, to specify z. And so this is the number of z. And what is written here? It is just log of all this stuff, log of the number of all potential z.
So it's application of coding theorem. If you want to prove that the complexity of z is small, you invent a way to generate z with high probability. And so you try random programs, and many of the programs produce some y, and then you apply a random program on y, and if there are many paths, the complexity of z drops.
Yeah, it's another way to say more or less
the same thing. Yeah.
There was just a computation of cardinality of the set of z's, but instead you can compute the probability of getting the z and see that it's large. Yeah, it's exactly the same idea. So, and also just to make we can recall how it the same version for if you have many program of given length, then the string is simple because simpler than this length, because there could not be so many strings, because all the programs are shared between them. So if you use a lot of them, you are in a small minority.
Yeah, and I see that when I confused Y and Z, Sasha Kazachinsky corrected me. So hopefully it was not completely unclear, since the audience can see my mistakes.
But how Sasha Kazachinsky mystically corrected this?
He wrote something in the chat. Don't worry.
Yeah. Sorry.
Okay, are we done with this lemma?
No, I think we can move and then return if needed.
Okay. And let us apply the first lemma to another also simple observation, another simple lemma. In lemma 2 we have two different clusters, S and S prime, with parameters m, or some parameters m and L. And assume that in the intersection we have many common points. Just the intersection of two clusters is large.
So for now, the size of each cluster is not restricted. We assume that it's large because intersection is large, but this parameter doesn't appear in the statement.
Yeah, just L, which is this log size of a cluster, does not appear in the statement. But we say that intersection of two clusters is large compared with the diameter. So you can think of D as something logarithmic, or even a constant. And in this, I claim that in this situation, we can take the union of these two clusters, and the union, I don't know, S hat, is also a cluster with a diameter with just a little bit larger. A little bit larger.
It's a bit confusing since you add to the union some new elements, but anyway, it's a cluster.
Where no, there are no new elements. You see, here it's all empty.
Okay. Okay.
All elements are. Okay, and it's just a direct corollary of our first lemma. Why? Just we take the union of two clusters, S and S prime. We want to show that the information distance between them is small. And what do we know? There are lots of points in the intersection. And for every point in the intersection provides us with a chain with a path of length 2 from this X to this Y. It must be Z to be like in lemma 1. And Y are points in the intersection between clusters. So the first jump from X to Y requires conditional complexity at most M. The second jump from Y to Z also requires conditional complexity at most M. And since there are lots of these Y, we conclude that the complexity of z given x is bounded by m plus a little overhead. Okay?
Yeah, even Sasha Kazachinsky proved an identity in the chat, which I now see now.
Yep. Okay.
But by the way, about the previous lemma, it would be funny to check whether it's true in real graphs. For example, in road graphs. So if we have a lot of not very short paths from x to z to some y, then there should be a very short one. I don't know it's true, but it looks kind of natural property of a graph.
I think it depends on a topology. If we have two big cities on the opposite sides of the globe, and we ignore the existence of oceans, then there must be roads going in all directions by all of those meridians.
No, of course it's not about distance, it's about roads. I would think that it would be strange that there are a lot of roads to the North Pole and to South Pole without having a very short road between them. Okay, but just...
Okay. It will be the last lemma where nothing happens. It's a corollary of the corollary of the first lemma about chains. The claim is that if we have some cluster S and some canonical cluster has no name, let it be S prime, canonical one, and they have a large intersection, then I claim that S is contained also in a canonical cluster, and not just arbitrary canonical cluster, but the canonical cluster with the same kernel, the same kernel that the same kernel from S prime. So let me remind that a canonical cluster S prime, we can think of it as some kernel, let us call it Z, and all these petals around Z. And now assume that many of these petals appear to be an S. Now I am saying that if we keep the same kernel but just increase a little bit the diameter, the size of petals around Z, then we will cover the entire S. Well, the same idea. If I take, I will change the color. If I take some point here in S, there are many two steps paths, two steps chains from the base, the kernel of the canonical cluster on the right to this point. It means that that complexity of this point in S, conditional on the base, on the kernel, is bounded by M plus a small overhead. That's the idea. Again, nothing deep happens. We employ once again the same simple idea.
Yeah, but you speak about the parameters of a canonical cluster, but canonical cluster has the kernel at a distance, yeah?
Canonical
Or
cluster.
you just consider the parameters with in the old way, the size and the.
No, a canonical every cluster has two parameters, the diameter and the size. A canonical cluster, besides these parameters, it has also some physical object, the kernel or the base, and all other elements are constructed as this base plus something of size m.
Andrei, but the base must be simple, conditional on any member of the cluster. So
With
why
some
this?
parameter,
Why this simple conditional to that leftmost string?
Okay. Just let me change again the color. Just draw these chains in the other direction. We have many chains from this x to z that go through different y. On this step, the complexity, conditional complexity is m. On this step, the conditional complexity is close to 0.
Ah, okay. M
So
plus
we use the
0
same
minus m.
lemma, but in different regime when the second complexity is small.
So it's all this looks like nothing. There is no real argument, but we observed the following fact. If I want to show that some cluster S, some arbitrarily cluster S has a kernel, it is enough to find a large intersection of this cluster S with some canonical cluster S prime with approximately the same parameters. And this is enough. So our goal now is to show that every cluster has a large intersection with a canonical cluster with approximately the same parameters. That's the idea. Okay, and now we're going to look for this. So we are holding some cluster S, and we are going to find some canonical cluster S prime with a large intersection with our S. How to do it? Just first question: where can we get all these useful canonical clusters? The first idea, which is pretty naive and pretty simple, even too naive. We can, if we know the parameters n and l, which is approximately m minus d, we can just enumerate all clusters in the world with these parameters. It is an infinite family of all clusters, but when we hold in hands some cluster S with these parameters, we can check it. It's an enumerable property. We can check that, okay, the size is something self-evident, and the diameter is a co-enumerable. We can verify that all conditional complexities are bounded by M.
But philosophically, you are looking for a canonical cluster with large intersection, and instead you enumerate all clusters. Why not all canonical clusters then? What is the motivation for that?
Okay, let us postpone this question.
Okay.
Let's postpone the answer.
Yeah.
Okay. For now, I can only agree that it looks ridiculous to enumerate just all clusters in the world. There are too many of them, and I suppose probably most of them are not canonical. So let us try to reduce somehow the set of clusters. First of all, it's if we're going to enumerate this, some reduced family of clusters, it seems useless to enumerate many times almost one the same cluster with different names. If we just subtract a couple of elements from a cluster or add one or two elements to the cluster, it's almost the same thing. We want to find clusters that are really different. So I'm going to enumerate really significantly different clusters. I'm going to enumerate clusters with a small pairwise intersection. And the small pairwise intersection will be understood just like that.
So what you say that you just take enumerate all clusters and keep only ones which have small intersections with all previous clusters, or what?
Yeah. Okay, let just before we go into technical details, let me try to give a kind of philosophical answer to your philosophical question. Why do we enumerate all clusters, or maybe some special subsequence of all clusters, when we need only canonical ones? Just imagine such an ideal situation. Okay, this is our cluster S, and I am enumerating clusters with minimal possible pairwise intersection. The hope is that at some moment we will enumerate a cluster which has a huge intersection with our S. And then we will say that, okay, these two clusters, they are almost the same thing, since they have a large intersection. And another idea, another thing
but
that I'm
now
going
this other cluster, if it would be canonical, it would be great.
Yeah. And another thing I'm going to say, that's the cluster that I will enumerate just by construction, they will be canonical. So if it is cluster 1, cluster 2, cluster 3, 4, 5, 6, 7, just the index of a cluster in this enumeration, it will be its kernel. The index of a cluster, we will see that the index of a cluster can be used as the kernel of this cluster, so it's kind of canonical. Okay, no, not kind of. It's canonical with reasonably chosen. Okay, how to say? It's almost a canonical cluster. It's a large subset of canonical cluster. So
and the kernel is
the index of this special cluster. Okay, if you want to be very, very, very formal, then it is not true literally, but this is true morally. I will enumerate some family of very special clusters with small pairwise intersections, each of them has an index in this enumeration. And instead of considering a cluster, I don't know, a cluster number k in this enumeration, I can take the canonical cluster with the base, where the base is the binary representation of the number k. It will be almost the same thing. It will be a really canonical cluster, which almost coincides with what we get here.
But you need to deal with strings that are in many of your enumerated clusters. So it can happen that so you're, do I understand correctly that you're using that a string can only belong to a few of the blue clusters?
It will be the main technical part of the argument. It turns out that indeed
Okay.
every point will be covered only by very few the special selected clusters.
Okay.
Now, also, if you look literally at what you are saying, there are infinitely many clusters, and for example, clusters with large long strings, and so all they are disjoint and of different lengths. So you have this numbering goes to very large numbers, and so our cluster. So something you need to deal with parameters somehow, probably.
Okay, formally, so it's a question about the statement of this lemma 4 or about the proof of the lemma?
It's about the proof. So you have these lemmas 1, 2, and so on, but they have logarithmic precision. And so Sasha is worried if your center becomes a huge number, then this exponentially big number compared to the strings that it contains, then your logarithmic precision will destroy everything.
No, but the logarithmic precision doesn't include the complexity of the string now. But just you say that if you find a canonical cluster which is good, it can be canonical, but it cannot be canonical with a very complicated. If the core is the number and number is very big, then this core cannot be simple given elements of S.
Yeah, so we will get somehow automatically that this selected cluster and the corresponding canonical cluster which has a large intersection with our S, complexity of its objects will be comparable with complexity of our with objects of our S. We will get it for free.
Yeah. Okay. So let's go on this argument.
Okay. So actually this picture with blue this things it's already a start of the proof.
So we do not assume yet that lemma 4 is proved. We are trying to prove it.
We are trying to prove lemma 4.
To be.
So now I am trying to explain the proof. Let us come back to this wrong too naive idea 1. We can construct a machine, an algorithm, which enumerates all clusters in the world with parameters m and m minus d, diameter m, and log size m minus d. So there is a machine which produce these clusters, C1, C2, C3, etc. An infinite huge family. And let us add a filter. Which will choose a subsequence from this flow of clusters such that the pair with intersection are small. We will choose this parameter d prime later. Just don't worry about it. Just when we get from this original machine, original enumeration, a new element, a new cluster C, we check whether it has a large intersection with at least one cluster which was selected earlier. If it has a large intersection with somebody who is already selected, then we ignore it, we don't take it. If it doesn't have a large intersection with any previously selected cluster, we take it as a new, another selected cluster.
So just a kind of greedy algorithm of constructing independent set. Nothing strange happens.
Yeah.
You do what you should do. Yeah.
And all clusters that will appear after this filtering, they are called selected, special or selected. And actually, this picture, the idea that this picture consists of only filtered, selected clusters. And now we need to prove that we need to prove that we need to prove that for selected cluster that its index can work more or less as its kernel. That is, complexity of this index is small given any element of the selected cluster. Or, more or less the same idea expressed in different words, what Bruno has suggested, every point, every string is covered by only very few selected filtered clusters. If we can prove this, we are done. This is the main goal. Just every string is covered by very few filtered clusters.
Therefore, we can find the cluster which we want just by comparing by looking.
So if a point is covered by 2 to the power order d clusters, then we need order d bits to specify the center given the point.
Yep.
Yeah, that's what it is.
And so this technical part remains unproven, but why it works? Why it is enough? Look at our original cluster S. I don't know whether it will be taken in this selected filtered subsequence or not. If it is taken as one of these filtered clusters, then it's fine. Then its index will work as its kernel. We're already happy. If not, then it will be not selected. Why it is not selected? There's only one reason why it is not selected. Because when it appears here in this enumeration, we will see that it has a large intersection with one of the previously filtered clusters. So it will have a large intersection with one of filtered clusters which has a kernel, its index. And again, we are happy. So it only remains to show that every individual string can be covered by only very few filtered clusters. And now I have a technical question. it seems that our time is over. Should we stop right now?
No, I think maybe we can finish this argument, and the second part can be continued next week, because it seems that you're more or less close to the end. It would be a pity to repeat everything again next time. If nobody has to go somewhere, maybe we can finish it now.
Okay, is it okay with everyone, or is it? Okay, okay. Okay, so here is the technical version of this idea, that if we have some point, if we have some string, then it can be covered by only few filtered clusters. Okay.
What is d prime?
D prime is it is the parameter from the definition of a large intersection.
And d is d is also the same parameter as before.
Yeah, d is the same as before, and d prime is this threshold between small intersection and large intersection.
I see.
So we deal not with some new parameters, but we just add an additional conditions to parameters d and d prime, which we have to use in the argument. So d prime should be more or less d over 2, yeah?
Or twice d.
No, just let's look on the d prime is twice d or twice d.
Twice d.
Okay.
Okay, so let us fix some string x, and let us look at the filtered clusters that contain it, that cover it. Look, all points in all clusters covering x, they have all conditional complexity at most m given x. So all these points, all these clusters, they live in this universe of all sets y, such that complexity of y given x is at most m.
Not sets, but strings just.
Strings. Strings. Yeah. And there are 2 to the m plus 1 different points in all this union. And
and each of them has size 2 to the m minus d, yeah?
Yeah. So these are clusters covering our point x. Their union is of size at most 2 to the m, or 2 to the m plus 1. And on the other hand, just I'm going to apply the formula of inclusion and exclusion. If there are n clusters here,
so we know that their intersection is small by construction, because we dropped the big ones, and
so
each of them is large.
We
so
know that
union
each of them is of size 2 to the
m minus
L,
d.
which is m minus d, and the pairwise intersection is n choose 2 times the large intersection, which is 2 to the m minus d prime. And I'm going to say that this gives a contradiction where n is large.
Technically,
wait, no, don't say anything. Okay, don't say anything. Okay, I will just rewrite this inequality. N times 2 to the m 2 to the minus d is at most n squared over 2 2 to the m, 2 to the min, oops, 2 to the minus d prime, plus 2 to the m, 2. I can simplify 2 to the m everywhere. And now I'm going to say a stupid thing, which is obviously wrong. I'm going to say that if n is large enough, then I get a contradiction. No, I don't get a contradiction. If n on the right we have n square, and on the left we have a linear function n. So when is huge, of course the right hand side is bigger than the left hand side. But when n is getting not terribly large, but okay, large compared with these two, we do get a contradiction. We can take n such that n multiplied by 2 to the minus d is bigger than these two, I don't know, maybe bigger than 3. The question, what should we do with this term on the right? And in this term on the right, we can choose this d prime. This is the moment where we really choose this d prime. We choose d prime such that 2 to the minus d is still bigger than n square. So once again, I choose n such that the term on the left is a bit greater than this constant 2 on the right. And I fix this n. And so basically it's 2 to the d, then 2 to the d plus a constant. And now I choose d prime such that this term, this term with n square, does not prevent us from getting a contradiction. Thus, the conclusion, what we have proven. We have proven that we get a contradiction if here in this picture with filtered clusters covering X, we have at least n different sets, at least n different clusters. So the conclusion, in reality, there cannot be more than 2 to the d filtered clusters. Okay, 2 to the d plus 1, 2 to the d plus 2 different clusters covering our point X.
Because if there are many clusters, we can remove some of them and get a contradiction.
Yeah,
right?
if there are huge number of clusters, let us take 2 to the d plus 2 of them. Let us take a few of them, n of them where n is not terribly large, and this will lead to a contradiction.
Yeah, so this is kind of most technical part, and one should look. No, I am a bit confused. You somehow at some moment you say that you change d prime, but d prime is somehow given.
Now, d prime is the threshold that we're free to choose. It's we can choose it in the way that is appropriate, and this is the appropriate way to choose d prime.
So, but if d prime is chosen in this way, then we don't need to consider only some of the, to decrease n, so to say.
We still need to consider. We still need to take only the right number of clusters covering this point. So I come back to this picture. So it was an explanation why each point can be covered by a a few but not too many different filtered clusters. It means that for every filtered cluster we have a kernel. It's more or less canonical. It's a subset of canonical. And it remains to say that the initial, the cluster S, has a large intersection with somebody canonical, and has a second it can be married with the kernel, with the index of this canonical cluster. The end of story. I think this is, yes, this is all. This is the end of the proof of the main theorem.
No, I guess that we should again look on the details and parameters. It's one cannot, at least me, I cannot follow this exact thing. So
No,
but the
I
idea
did.
is clear, and if it works, then it should be not difficult to show.
Yeah, actually I didn't assume that you will follow very precisely all this computation with parameters, but indeed it seems that when the idea is clear, you can reconstruct it yourself if you need it.
So let's say it's technical things. So first to prove that something is a part of canonical cluster, we say that it has a big intersection with some canonical cluster. And to find this intersection, we construct a node that if clusters are almost disjoint, if we select only almost disjoint clusters, all of them are canonical. And then if our cluster is not selected, then it should have a large intersection with some of them, and so it's more or less canonical because of this last argument with small multiplicity of covering.
Yeah, you're right.
Something like this. Okay, so for Bruno, for example, is the idea clear? Yeah.
Yes, but you sometimes say that proofs with two cases are not nice. And here we have two types of clusters, the canonical ones and the non-canonical ones. So then one can wonder, is there more direct proof?
Where we have two types of clusters.
So the theorem says for every cluster, there exists a center.
Yeah.
Or a kernel. And then the proof considers two cases. Either the cluster is a canonical one, and then the construction says it's the index and the enumeration of canonical clusters, and otherwise you pick the one where it's sufficiently close.
It's not really two cases. We just say that there exists a canonical cluster with large intersection. If it just coincides with it, it's not a really different case. It's just a limit, ultimate case of big intersection. So I think this is not.
Yeah, we can say that indeed. To have an intersection with a canonical cluster, it's more or less the same thing as to be a part of canonical cluster. What is really going on in this non-trivial part of the proof? We're saying that these filtered clusters are somehow, by some miracle, all canonical. So we're saying that the index of filtered clusters can be used as the center or the kernel of this cluster. This requires some combinatorial argument, and here we used the fact that every string is covered by only a few filtered ones.
Yeah, and this I could follow.
This is the only moment when we pretended that some clusters might be non-canonical. This is when we say that, okay, we have an index, and because of this small intersection property, the index can be used as a kernel. here is the moment when for quite arbitrary filtered cluster, we say that we can explain what its center, its kernel is. Questions? Comments? Complaints? Critics?
No, I think that we will next time we can continue with the second part. That's not only an abstract result about clusters, but has some consequences for finite strings and properties of finite strings.
Wait, when is the next time? I think next Monday, two of us, you and me, were not available for a seminar.
To me, I'm also will be busy in next Monday.
Oh, it's a still conference actually, yeah, next Monday.
No,
so
not conference. I will have a seminar which will be moved from Tuesday, because Tuesday is March 8th. It's a holiday in Russia.
Okay, so then it's let's make it 14th. No, it's not really serious to plan for such a long time, but if nothing happens...
2 weeks. Is it correct that the kernel of the cluster can be defined as the maximal I, such that we can choose to the I clusters before it with small pairwise intersection? Yeah, agree. This is true.
Mm-hmm.
So it's quite unusual kind of proof. The source, when we construct some object, usually sometimes we say that there exists something with some property, but the source of constructing this object is a bit strange. We enumerate some extremely large, exponentially large things, and then still somehow get find a small string out of them because of this thing. But yeah, okay.
Oh, so I'm not so sure if the answer is yes to Alexander Kozaczynski's question.
Why
Because
not?
we consider greedy algorithm, maybe there exists a different algorithm of picking clusters, non-greedy one that can find more clusters that are pairwise disjoint.
Oh, okay. When I say yes, I mean this specific greedy algorithm.
No, there can be a more clever algorithm where you can have more clusters that are pairwise disjoint.
Yeah.
So it's not so clear whether the answer is yes.
No, just for an arbitrary algorithm.
If you fix the algorithm,
idea,
it's true. But that's not how I read the question.
Yeah, indeed. Just if we take an arbitrary algorithm, then I don't know.
Yeah. Okay. So
Okay.
then let's stop now and wait. Hope that we will still be able to meet in 2 weeks, which is not obvious, but
You're worried about nuclear war, Sasha.
No, or other events in Russia,
okay, yeah.
And then
I will say concerned.
Yeah.
Yeah. So at least I may